packaging area. In the automotive area, natural fiber composites are mainly used for interior trim structures, and these are also referred to as secondary structures, which means that these are the known load-bearing parts in a car. So the natural fibers in South Africa. South Africa is world's third largest biodiverse country, and we have an abundant supply of fibers. We've got flax plantations in the Western Cape. There was a canal plantation in KwaZulu-Natal region. We also have indigenous fibers like wild silk. We also have animal fibers like wool, cashmere and mohair, and I believe we are the 12th largest producer of wool fibers. So how do you use natural fibers in composites? Now, they are mainly can be used in three forms. You can use it in short fibers, in the form of short fibers, non-wovens, or woven fabric. Now, non-wovens are made by three main techniques. One is needle punching, where non-wovens are actually fiber mats. So there is no weaving, it's just a fiber mat. And the bonding is created by these three techniques. So in needle punching, bonding is created by mechanical interlocking, because the fiber mat is passed through a conveyor belt and you have needles moving up and down the fiber mat. So that creates mechanical interlocking and the bonding. Then another technique is hydro-entanglement. And in hydro-entanglement, water jets at high pressure and of extreme purity are falling onto the fiber mats, and that creates the bonding within the fiber mat. And hydro-entangled non-wovens are very soft and smooth to touch, and they usually have applications as tissues and wipes, diaper linings, and so on. In chemical bonding, you actually have a synthetic fiber along with the natural fiber, and this mat is allowed to pass through a heater where the synthetic fiber, like polypropylene, would melt, and that creates the bonding in the non-woven. The advantages of non-wovens is the high aspect ratio, which is a length diameter ratio, its strength and flexibility, and non-wovens are majorly used as interior trim structures in automotives. So this is our non-woven pilot plant of the CSIR in Port Elizabeth, and here we can develop a variety of customized non-wovens for industrial applications as well as for use in composites. So the first picture on the left shows the fiber mats, the non-wovens. The picture on the right, the top picture on the right, shows the needle punching unit. And below you can see the hydro-entanglement unit, and further on where we can do thermal bonding and calendaring and so on. So we'll just go to the first project, which was the development of sandwich panels. And this project was in collaboration with a leading aircraft manufacturer. The aim was to develop natural fiber reinforced composites, mainly sandwich panels, for secondary structures in cabin and cargo areas in aircrafts. Secondary structures, as I mentioned, are non-load bearing parts. So it mainly refers to the side walls, the side wall panels in aircrafts. Now, sandwich panels are used very much in aircrafts. You have glass reinforced phenolic sandwich panels are mainly used in the side panels, and glass reinforced epoxy is used for the floor as well because of greater strength requirements. So currently, as I say, that the side panels are made from glass reinforced phenolic resin, and the purpose of the project was to replace the glass with a woven flax fabric. So phase one of the project was to focus on a phenolic resin, which is a thermoset matrix, and then phase two was to replace the phenolic with a bio-based thermoset matrix. And here we used polyfurfuryl alcohol resin as the matrix. And the challenge was to maintain the balance between strength and FST requirements, which is the flame flammability requirements. I think I've gone through this before. Why biocomposites in aerospace, energy and environmental concerns, lightweighting, which is an important consideration in all transport sectors, because lightweighting automatically translates into fuel savings and energy efficiency. The cost of petroleum-derived materials, Clean Sky Initiative, REACH, and how carbohydrate economy is important for developing countries. So the key criteria in aircraft performance is lighter, faster, and environmentally friendly. And here you can see the sandwich panels that were developed. Now, the first step here is that one of the most important requirements in the aerospace sector, even more important than mechanical strength, is the flammability requirements. It's the flame, smoke, and toxicity requirements. So here we had to impart the flax fibers. Natural fibers, as you would know, is highly flammable. So we had to impart the flax fibers with an environmentally friendly flame retardant treatment. And that was the first step. And after treating it with FR, these flax fabrics were then coated with the phenolic resin. So in the first picture, you can see the prepregs and the Nomex code that was used. Now this prepregs is then compression molded at the right temperature so that the curing of the phenolic resin occurs. And on the right, on top, you see the sandwich panel where the skins, top and bottom skins, are woven flax with phenolic, and in the middle you have a Nomex core. At the bottom you have top and bottom skins from woven flax reinforced polyfurfuryl alcohol resin, and in the middle you have Nomex core. Now these are the aircraft requirements, FST standards, and the flammability was measured in two equipments. One is the cone calorimeter and the other one was the Ohio State University heat release apparatus. Now both equipments measure the flammability, mainly the heat release in a material while burning, but the principle of measurement is different. Cone calorimeter is based on oxygen consumption of the sample during burning, while OSU is related to the thermal flux of the sample while burning. Now, according to FAA regulation, which is the Federal Aviation Admin Regulations, it is mandatory that if you want to use materials in aircraft, it has to be tested on the OSU. So that's why we've tested on both the cone and the OSU. The mechanical requirements comprised of a 4-point bending test and a peel test. And and we also had to make sure that the weight did not exceed that of the current panel. So this is just a picture of the cone calorimeter and the parameters one can get from cone calorimetric testing. You can get the heat release rates, the heat of combustion, the smoke release rates, the concentrations of gases like carbon monoxide, carbon dioxide, and oxygen, how much time it takes for the sample to ignite, and mass loss. So on top, you have the picture of the cone calorimeter. Bottom left, there is the sample in the holder. And on the right, you see the sample while it's being tested in the cone. So these are the flammability results from the OSU testing. And this graph shows the peak heat release and the total heat release of the different panels. And the FAA limit, which is the Federal Aviation Admin limit, is 65. So the heat release, so for a material to be qualified to be used in aircrafts, the peak heat release and total heat release should be equal to or less than 65. Now you can see a number of panels here, and all the panels are basically a flax phenolic system, but for some of the panels we have used an adhesive. In some we have varied the amount of flame retardants. We have used different types of flame retardants in some. In some of the panels, we used a non-woven. Instead of a woven fabric, we used a flax non-woven. And in panel 15, we used two types of flame retardants. So the primary flame retardant treatment was on the flax fabric, while the secondary flame retardant treatment was added into the resin in certain cases, and in certain cases it was added as a coating onto the panel after the panel was taken out of the compression molding press. And you can see that most of the panels are below the 65 limit of FAA, and panel 15, which comprises of two types of flame retardant treatments, shows the minimum value for both BHR and THR. Now these are the results, flammability results from testing done on the cone calorimeter. And here the variations in the panels are panel 15 to 17, the secondary flame retardant was applied as a coating onto the panel. Panel 18 to 20, the secondary flame retardant was added into the resin before making the panels. And all of the panels are meeting with the FAA limit, and it's actually pretty low. It's sitting at 8, while the limit requires it to be 65. Then as per FAA limit, the total smoke release should be 200 or less than 200. So as you can see, all the panels are complying with the limit. In terms of flexural testing, the requirement was that the ultimate bending load should be greater than 350 newtons. And then you have here most of the panels meeting with that requirement except for panel 8. So this is just a picture of the panels before and after testing. So on top you can see the panel. Below left you have the flame retardant panel, and you can see that even after burning, the panel is compact and has not collapsed. While a panel without any flame retardant is completely collapsed. So it's also important that the flame retardants that you do choose is helping to maintain the compact structure of the panel. So this is the peel test, and the peel test basically measures the adhesion between the skins and the core. And the requirement was that it should be greater than 30 newtons, and you can see panel 15 is well above the requirement. So next we move on to the next project. So because we had met with the stringent requirements in the aerospace sector, we decided to extend this technology to develop panels for railway carriages. And here, while in the early case we used the expensive Nomex core, here we prepared the sandwich panels from, again, woven flax and phenolic resin. But the cores used were balsa core, which is a type of wood core. You have Nitaplast, which is a polypropylene core, and then you have a cardboard. So the processing technique was the same. Prepregs were formed. Prepregs were then compression molded at the right temperature to form the panels. So this is the testing of the panels, and this was done according to EN 545, which is the European standard for fire safety in railway carriages. And here, the MARHE, which is the maximum average rate of heat release, was found to be lowest for the sandwich panel containing the balsa core. And this was falling into the category of HL1 and HL2, which shows the hazard levels. Now, this is the mechanical testing of the panels. And again, you can see that the panel containing the balsa core exhibited the highest modulus as well as the maximum load. The maximum load was 509 newtons, while for the aerospace, for the panels that we developed for the aerospace sector, the load that was required it just needed to be greater than 350. So here, I would also like to say that, the panels that we developed, we also tested it according to the standards it needs to be tested. So if you are developing a panel or a material for aircrafts, then it has to be tested according to the Federal Aviation Admin regulations. If it is for railways, then you would use another standard. So that is very important because then your research and your science becomes relevant. So it is not just enough to do normal mechanical, thermal, DMA, DSE. It's important to develop, especially when you're developing a component for an industrial sector. Okay, then we come to the interior trim structures, and this is some work that we did for automotives. Now, in the earlier cases, we developed sandwich panels. So here, what we did was we developed non-wovens, which were then compression molded to form the laminates. So here, our collaborating partners were the VW and Mercedes-Benz. And while the science was important, another aspect of this research was South Africa is home to a number of OEMs, original equipment manufacturers, and the automotive sector contributes to about 3.4 billion to SA's GDP. But if you look at the number of local components being used, it is very low. It is sitting at 30 to 40%, and most of the components are being imported. So the government has started a program called the APDP program, which is called Automotive Production and Development Program. And the aim of that program is to increase the content of local materials in cars, in automotives, to at least 70%. So This project also supports the government's strategy of content localization in the transport sector. This is just a slide to show that in the European automotive industry, it's flax, which is being highly used. About 50% of the natural fibers that's being used is flax, followed by kenaf at 20%. And I think I went through this earlier. You have all these bio-based incentives and legislations which is supporting the move towards bio-based materials in the transport sector. The end-of-life vehicle directives, the fuel economy standards, carbon dioxide emission values. It has dropped from 130 gram to 95 grams per kilometers. So this is all supporting the move towards greener materials. And this is just a slide to show the importance of bio-based incentives and environmental legislations. Because if you look at this graph, you can see that the production of materials of natural fiber composites in the automotives is sitting at 350,000 with bio-based incentives. And if you don't have bio-based incentives, it actually falls down to 120,000. So again, goes on to show you how important incentives and legislations are. So these are the interior trim structures, and here there were mainly two aspects. One is we had to develop nonwovens in our nonwoven plant, and we used three types of combinations. One was a flax polypropylene, flax, then we used a hybrid flax kenaf reinforced polypropylene and kenaf polypropylene. So these are needle punched nonwovens. So these needle punch nonwovens are first tested, and they have to comply with the specs that's given to us by the automotive manufacturers. And then the needle punch nonwovens are compression molded to form the composite laminates. And the laminates also need to comply with the requirements. So this just shows the tensile results of the nonwovens that we developed. So the requirement was that the tensile strength should be greater than 1,150 newtons. And as you can see, all of the nonwovens that we developed are meeting with the requirements. And examples of secondary structures or interior trim structures are, the parcel trays, the door liners, the side liners, and so on. So this is an example of one of my PhD students. This is the work of my PhD student who is hopefully submitting this December. So another application area for natural fiber composites is that in the sporting goods arena, and some of the examples include like skating boards, ski boards, hockey sticks, and so on. And currently, some of the ski boards are made from carbon fibers, lightweight carbon fibers. But the problem with carbon fiber, apart from the cost, is that there's a lot of vibration while it's being used, and also carbon fibers undergo shattering or extreme breakage when it is subjected to high impact force. So the next step, so currently what people are using is a hybrid mixture of flax and carbon fiber. So my PhD student prepared these surfboards using sandwich panels of flax epoxy skin. So the top and the bottom are flax impregnated with epoxy and balsa core. Now, the processing technique was wet layup followed by vacuum infusion technique. And the main observation was that if you use a hybrid structure or assembly of flax with carbon, then there is improved impact and flexural strength. So the top picture just shows the number of surfboards that he has made, and then the bottom shows you him validating this technology in the real environment. So some of the conclusions in this thematic area is that natural fiber-based sandwich composites, they are promising materials in industrial applications, can be used in aerospace and automotive, and the building and the sporting industry as well. Now, if you want to use natural fiber composites in advanced industrial sectors like the automotive, aerospace, it is important to impart flame retardant treatment. And the FR treatment that we used was successful in complying with the Federal Aviation Amendment requirements and can be applicable to other sectors as well. We also have a joint IP with the aircraft manufacturer on the development of the flame retardant sandwich panel. This project also helped us to establish an accredited fire testing facility at the CSIR. So the fire testing lab at CSIR hosts a number of equipments. We have the cone calorimeter, we have the OSU, which I mentioned. If you want to use materials in aircraft, it's mandatory that you test material in an OSU. Yeah, that's all. Okay, the next slide talks about the conversion of agro-industrial waste residues to bio-based composite products. So just a basic definition of biomass, it's an organic material of microbial, vegetal, or animal origin. Now, biomass can be classified into different categories. You have industrial waste, and this is an example for industrial waste is sawdust. Agricultural waste, and here we are actually focusing on post-harvest agricultural waste residues like maize, stover, bagasse, and so on. And then you have forestry waste, which refers to the chips and the barks and the leaves of the trees. Now, the picture that you see below just represents that if you take industrial mass and subject it, industrial biomass, and subject it to various conversion technologies via chemical or thermochemical or biochemical, you can get an array of products like biofuels, bio-based materials, and energy. Now, this is the principle of a biorefinery. Now, as you would know, a petroleum refinery, you have petrol as a feedstock, and the petrol is then converted to different products, starting from fuel to material to energy. Now, a biorefinery, you have industrial biomass as the feedstock, and that is converted to a number of products using various conversion technologies. Again, what is the advantage of agro-waste residues? They are abundantly available. They are comprised of valuable materials like cellulose, hemicellulose, and lignin, and therefore they are a renewable feedstock from which you can derive several products. They are considered as waste. They are not waste, but they are considered as waste, and therefore there's no competition with food crops. And currently, if you look at what's happening with the agro-waste residues, some of it is being used as animal fodder, but most of it is incinerated or left or just dumped in the landfills, which creates more environmental problems as well. So if you look at the South African scenario, the South African maize industry is the largest in Africa. We have an annual production of 8 million tons and 3 million hectares of land. And the waste from this production comprises of cobs, leaves, and stalks. And there's plenty, there's millions of waste, millions in amount that's left behind. So there's plenty that's available for developing different kinds of products. If you look at the sugarcane industry, we have 14 sugarcane milling companies. And the waste from that is referred to as bagasse. Now, here most of the bagasse, about 50% of bagasse is now used as a fuel in the sugar mills, but there is plenty available because from 10 tons of crushed sugarcane, you can get 3 tons of bagasse. So in some of our projects, we have used maize and bagasse to develop further products. So yeah, so this picture shows in a nutshell how you can convert waste into value-added composite products. Now, as I said earlier, waste biomass residues, be it agro or industrial, is composed of cellulose, hemicellulose, and lignin. Now, and what are the products that one can get from cellulose? Cellulose, by means of treatment and acid hydrolysis, you can get nanocellulose, which is one of the most interesting bio-based nano-reinforcements around. Hemicellulose is a mixture of sugars, and the C5 fractions of hemicellulose are very interesting because you can extract xylene from the C5 fractions, and xylene is a biopolymer which has applications in packaging. Another interesting chemical is furfural, which I think even the earlier speaker referred to. Furfural can be converted to furfural alcohol, which can be polymerized to give you polyfurfural alcohol resin. So this is one of the this is a thermoset resin, and you don't have great many examples of bio-based thermoset resin. So PFA is interesting thermoset resin. Then you can also extract hydroxymethyl furfural which can be converted to FDCA, which is furan dicarboxylic acid. And that, when polymerized with ethylene glycol, will give you polyethylene furanate. Now, currently, Aventium, a company in Netherlands, is planning the industrial launch of PEF, which is polyethylene furanate, somewhere in 2023 or 2024. And it is assumed that once PEF is launched, it is going to replace the PET in drinking bottles. Now, PEF is supposed to have improved properties than PET, but PET, and it is 100% bio-based. It's completely derived from plants, and it is not biodegradable, it is recyclable. And then from lignin, what can you get? Lignin is, as I've mentioned before, is a aromatic macromolecule. It's composed of phenolic moiety, so you can extract bio-based phenolic resins from lignin. Or the other thing that you can do with lignin is a highly cross-linked structure, so it has inherent flame retardant properties, and you can use it as a filler in composites. So based on the different materials that are derived from the waste, and again by different combinations and permutations, you can get a number of novel bio-based composite products all derived from waste. The properties of cellulosic nanomaterials, very similar to natural fibers, high strength and stiffness, it is chemically stable, it's biodegradable, biocompatible, and also it's got reactive hydroxyl group, so you can do a number of modifications onto the cellulosic nanomaterials. Now, this is an example of a product derived from cellulose. So this is a cellulose nano paper, which we developed in collaboration with Luleå University of Technology in Sweden. And here, nanopapers were developed from both cellulose nanocrystals and cellulose nanofibers. And in the first case, the cellulose nanomaterials were extracted from microcrystalline cellulose, and the nanopapers were formed from the cellulose pulp by casting and evaporation. And you can see that the nanopapers prepared from cellulose nanofibers exhibit higher strength than that from CNCs, mainly because of the interfibrillar network in these materials and also the hydrogen bonding present. And these have high strength and modulus, and they can be used for packaging applications. So this is also another example of a product that can be derived from cellulose nanomaterials. And this here, our collaborating partner is Stockholm University in Sweden. So here the idea was to develop bio-nanocomposite fibers from cellulose nanoviscose and polylactic acid. So here the first step was to prepare a master batch of polylactic acid and cellulose nanoviscose, and then this was then placed in the extruder and dry mixed with PLA to get the ratios right. So here you can see the picture of the extruded pellets, and these extruded pellets are then placed in the filament extruder to get the PLA fibers. So as you would know, nanocomposites, you would usually get it in the form of either dumbbell specimens or rectangular specimens. But here you have a nanocomposite which is in the form of a fiber, and the nanocomposite is cellulose nanoviscose reinforced PLA. And some of our important results are that we saw improvement in thermal stability by the incorporation of cellulose nanoviscose. The thermal shrinkage of the nanocomposite fibers was much lower, so this has applications in the textile arena. There was also improved crystallinity. Now, the possible application is that these fibers can now be converted into nonwovens. And then you have a nanocomposite nonwoven mat, which can be used for self-reinforced composites. Another option is that while you are extruding it in the filament extruder, while you're forming the fibers, you can add additional ingredients, additional functional agents. It can be flame retardants, it can be antiviral agents, so that you have functionalized nanocomposite nonwovens. And an example is that you can use these functionalized nonwovens for making filters in masks and so on. Then we come to lignin, and lignin is, it is the second most abundant biopolymer. It is a byproduct of the paper and pulping industry. And you can see it is composed of phenyl propene monomer units. In some of our work, we used lignin as a filler in PLA. The processing technique was melt compounding followed by injection molding. The problem with lignin is that there is an issue with dispersion of lignin in biopolymers, and one would have to use coupling agents or compatibilizers to improve the dispersion. So though we notice an improvement in modulus, that is mainly due to the volume content of lignin, in order to get good tensile strength, one often has to use coupling agents. Other applications of lignin, and a very interesting application, is the development of bio-based carbon fibers from lignin. Currently, carbon fibers are derived from PAN, polyacrylonitrile, which is petroleum-based, and which is also very expensive. So there are projects right now where people are thinking of using lignin to develop the carbon fibers. So then you have a bio-based feedstock for the development of carbon fibers. You can also, as I mentioned earlier, lignin has a number of phenolic groups, so you can extract or derive phenolic resins, bio-based phenolic resins from lignin. This is again my work of my PhD student. So this is about hemicellulose-based products. Hemicellulose, as I said earlier, is a mixture of C5 and C6 sugars, and one of the most important fractions is xylans. Xylene has good barrier properties, and it can also form films, usually when you are blending it in another biopolymer. So my student, his work entailed of extracting the xylene from the maize tuber and then blending it with natural biopolymers. So I think the biopolymer that he chose was alginate, which, as you know, can be obtained from seaweed as well. And the films are formed by solvent casting technique, and films were also formed by adding clay as well as cellulose nanofibers. And I think for the films which contain cellulose nanofibers, we noticed improved strength and modulus. And this was mainly attributed to the interfibrillar network in cellulose nanofibers. Now, xylene also has applications. So this has packaging applications in the packaging sector, especially can be used for development of edible packaging films. So this is another example of where we developed a product from nanocellulose. So here the polymer matrix that we use was furfuryl alcohol, and during the polymerization of furfuryl alcohol, we added the cellulose nanoviscose, and we got the PFA composite comprising of cellulose nanoviscose. Now, as I mentioned earlier, polyfurfuryl alcohol is an important resin. One is it's a bio-based thermoset resin. Secondly, it has a highly cross-linked structure, so it has inherent flame retardance, which is very important. So it has applications in automotive and aerospace sector. So here, if you would look, you can see that both the matrix and the reinforcement can be derived from waste. So it's a completely waste derived product. This is another example of a project where we use nanocellulose, and our collaborating partner was University of Vienna in Austria. And here we use nanocellulose as a binder. So here, first step was to prepare natural fiber nonwovens, which we did in our nonwoven pilot plant. And I think we used agave fibers. And then these nonwovens were coated with a natural fiber with a nanocellulose suspension. And then it was heated to form the solid structure that you see here. So there is no external polymer matrix here. It's just an all cellulose composite, one could call it, because it just comprises of the natural fiber nonwovens and a nanocellulose coating. And the Austrian partners, they tested these materials for use as composite filters for the removal of heavy metal ions. I think we published a paper last year on that, and it was found to be quite successful. Okay, this is 3D printing of bio-based materials. So this is also the work of one of my PhD students. So 3D printing, is commonly referred to as a sustainable manufacturing technology. And the advantages of 3D printing is the lower cost, larger design flexibility. You wouldn't, compared to conventional processing techniques like injection molding or compression molding, you don't need big molds. There is less waste, low energy demand, and then of course the rapid prototyping. And also nowadays we can get these desktop 3D printers as well. So here my students' work deals with developing 3D printable bio-based material. So his material is cellulose nano viscose reinforced PLA nanocomposites. So the applications of 3D printed materials is usually seen in the biomedical, educational, building and toy manufacturing sectors. But now, you're really limited by your imagination, because currently we have filament compounders. So you have companies or industries that are selling filaments, 3D printable filaments. And if you have a 3D printer at home, you can print whatever you want to. The common materials used for 3D printing is ABS, petro-based ABS, and in the case of biopolymers, it's PLA. And it is estimated that this market or this sector is going to witness huge growth over the next 10 years. So this is my PhD student's work. So his starting material is actually sawdust, from where he extracts the cellulose nanofibers. And then the cellulose nanofiber is mixed with PLA in a twin screw extruder to get pellets. And then these pellets are then drawn into filaments in another extruder. And these filaments are then used to 3D print a number of products, as you can see here. And when we looked at the properties of the developed 3D printed bio-based filaments, it was found to be compatible with the natural fiber filament that's there in the market. An additional advantage was that we saw that the processing temperatures that we used were quite low when compared to that of the market. So some of the conclusions here are that the biomass waste residues can be fractionated to obtain components like cellulose, hemicellulose, and lignin. And these can be successfully converted into value-added bio-based products. Some of the products that we have made from these fractionated components are nanopapers, xylem films, bio-nanocomposites, 3D printed bio-nanocomposites, and so on. And thirdly, sustainable materials and technologies are in sync with circular economy principles, and it is critical for development and growth. So before I end, I just want to go through the composite facilities and testing that we have here at the CSIR. We have the state-of-the-art facility for processing and characterizing bio-based materials. Our processing lab comprises of compression and injection molding, extruders. In terms of liquid processing techniques, we have the VAR, TM, and vacuum infusion facilities. We have a complete range of characterization possible in our characterization lab. Our fire testing lab, as I mentioned earlier, comprises of the cone, the OSU, smoke density chamber, limiting oxygen index tester, and a toxicity tube apparatus. We also have the biodegradation testing facilities, and we can do various tests there. One is the hydrolytic degradation, ecotoxicological studies. And that is basically for compostable materials. It is a requirement that the residue that's left behind should not be toxic and should be fit for plant growth. So we can do those kind of tests there. And thirdly, the mineralization studies. So as per ASTM standards, for the material to be claimed as biodegradable, it's not enough that it should just disintegrate or fragment. It is necessary that 90% of the carbon in the material should be converted to carbon dioxide. So mineralization tests measures that. It measures the amount of carbon dioxide that is emitted from the material during biodegradation. So these are some of our collaborating institutes. You can go through the list. Acknowledgements to all our funding agencies. DSI is our Department of Science and Innovation, who's our major funder. And then we have National Research Foundation programs as well. So this is our team, the people behind most of the work. I would like to especially acknowledge and thank Dr.Naveen Kulkarni and Amrita Vishwavidyapeetham for inviting me for this conference. I would also like to make a point that the students, the young students, and who are interested in a career in research, can take up postdoctoral fellowships in South Africa. We have a TWAS and RF fellowship. Also, I have affiliation at the Nelson Mandela University as well as at WITS, so we can plan PhD programs or postdoc fellowships through the university as well. And with that, thank you all. Thank you all for your patient hearing.
Thank you very much, Dr. Maya, for walking us through this wonderful research you're doing at CSIR Pretoria. Would be maybe next time we would be happy to have you here in person and interacting with our students. So I know it's 1:10 lunchtime for everybody, but then maybe we can take one question. If anybody wants to ask a question, please raise your hand. Okay, I think, yeah. If not, I think let's all thank Dr. Maya for her time and this wonderful talk. Thank you very much, Dr. Maya.
Okay, thank you so much. Thank you so much, Naveen, for inviting me. And I look forward to collaborating with you and your institute.
Thank you. Thank you very much.
Okay, thanks. Bye-bye.
So, thank you. So, I think we will close the morning session here. We will be again meeting at 2 p.m. with Professor P.B. Arvind from University of Groningen, the Netherlands, giving a plenary talk. And then from 3 o'clock, I just want to remind you that we have 2 oral presentations running in parallel. We have material science division and the green chemistry streams running. And then after the oral presentation session, we will be going to the valedictory function at 6:30 p.m. today. So where I request everybody to participate. So we will be announcing the best presentation awards for all these streams in the valedictory function. See you all at 2 p.m. Thank you. Thank you one and all.